Hello all. Today we are going to discuss the experiment feather analysis using GM counter. The aim of our experiment is to determine the endpoint energy of the beta particle from a given source using feather analysis. Geiger-Müller counter, which is commonly known as the GM counter, is one of the oldest and widely used radiation detector. It is also known as Geiger tube. It is actually a gas-based detector which uses ionization of gas by radiation as a primary tool to detect radiations. It detects ionization radiations such as alpha particle, beta particle and gamma rays using the ionization effect produced in the GM tube. It is filled with an inert gas such as helium, neon, argon at a low pressure to which high voltage is applied. Actually, it is a tube in the form of a cylinder which is filled with the noble gas at low pressure. A metallic string, we can see a metallic string which runs through the central axis of the cylindrical shape which forms the anode, whereas the outer shell serves as the cathode. Any radiations incident on the tube will ionize the noble gas inside it. The electrons thus ejected will get attracted towards the anode and the heavy ions will move slowly towards cathode. These charges will further ionize more number of atoms and thereby setting up an avalanche of ions and electrons which set up a discharge current there, and the current causes the voltage between anode and cathode to drop, which the counter detects as a signal since here the detection is based on the avalanche. The output pulse is independent of the energy brought by the incident radiation and the pulse height remains the same irrespective of the energy of radiation, and therefore the GM counter can be used to detect the presence of a radiation but not the type of radiation. That is, we can only detect the presence of radiation given to the GM counter, not the type of radiation. And in general, the GM counter is a detector of ionizing particle produced due to ionization by a high energy particle passing through the gas. Here the number of count per unit time recorded by the counting device is a function of electrode voltage. Hence there will be variation in the count rate with the voltage of a standard radiation source, but in the GM counter we measure the count rate according to the applied voltage, and the relation between the count rate and the voltage applied to the count is called characteristic curve. Here we can see a plateau graph of the GM counter with the x-axis marked with the applied voltage and the y-axis with the count rate. There is a proportional region in which the count rate increases with the applied voltage, and thereafter it comes to a constant value which is called the plateau region, and then it goes to the continuous discharge region. From this curve we can deduce the characteristic voltage, that is, it is the minimum voltage applied to the detector in order to operate, and the plateau length is the range of voltage corresponding to the flat portion of characteristic curve, that is, the constant region. The length of the constant region is called the plateau length, which is the highest voltage applied voltage minus the lowest applied voltage. And we get the operating voltage with which the GM counter works to detect the counts from this graph by which is the midpoint of the plateau region, that is the output operating voltage VO is equal to the plateau length, maximum of plateau length plus minimum of plateau length, that is V1 plus V2 divided by 2, which is the midpoint of the plateau region. And Here we want to determine the endpoint energy of the beta particle from the given source using the further analysis method. For this, when a nucleus changes its state by beta decay, the energy spectrum of emitted beta particle is extended from 0 to the maximum energy E0, which is called the endpoint energy. And if this beta particle pass through the material such as aluminium, some are absorbed. The number that are absorbed depends on both the energy of the particle and thickness of the material, that is the thickness of the aluminium we use here. And it is possible to define a quantity R as the range which is equal to the distance at which the beta particles are absorbed multiplied by the density of the absorbing material. That is, range is defined as the thickness of the target material penetrated by the particle. Range of the beta particle is given by R equal to 0.542 E0 minus 0.133. This is the further equation. We use this equation to find out the endpoint energy of an unknown particle, and where E0 is the endpoint energy of the known particle, and the endpoint energy E0 for various beta source can be found using this equation. And once E0, the endpoint energy, is known for a standard source, we can determine the range of the beta source. That is, to determine the range of unknown beta source, we use the formula range of unknown equal to x half of unknown into range of standard source divided by x half of standard source, where the x half value of unknown and standard is measured from the graph which is plotted with count per second along y-axis and thickness along x-axis. And actually the half value thickness x half is the thickness of the absorber, for which the value of intensity, that is the count, become half of its initial value of absorbed. The intensity, that is the count, I0 by 2 is the half value thickness, and it can be determined by rearranging the formula further equation using E0 equal to range of standard plus 0.133 divided by 0.542, and then we want to determine the endpoint energy of unknown source. By obtaining the range of unknown source, we can determine the endpoint energy of unknown source using the equation range of unknown plus 0.133 divided by 0.542. Here the procedure that we follow are, first of all, we have to determine the operating voltage at which the GM counter works. Operating voltage is the voltage which we set on the apparatus. First of all, as the preliminary adjustment, we make the connections and place the source facing the end window of the detector. Now we want to, this is the apparatus used for the experiment. We have to start with the power up the unit and select the menu option to program on the keypad of the GM counter, and select the present time and set the required time, that is we here use a time of 10 seconds. Set the time of 10 seconds using the arrow buttons that we see on the picture. Then press the start button to record the counts and gradually increase the HV by, that is the voltage, by rotating the HV knob. This is the HV knob. And then change the voltage. Take a fresh reading, that is a starting point, and record the observation for each HV set, and counting continues until the rate of the count suddenly increases. This is the discharge region of the GM counter, and a graph is plotted between the voltage and the count, and the operating voltage is found. Then we set the operating voltage that here we have obtained from the graph on the GM counter apparatus, and then the beta source, which is a non-source, is placed inside the apparatus, and then the absorber which we use here, aluminum, is placed. Then the counting starts with then the count is taken for every 10 seconds, and the operating, after determining the operating voltage, we set the operating voltage, and then the beta source, for which the range has to be determined, that is the standard source is placed. Here we use the standard source as thallium with an endpoint energy 0.766 mega electrovolt. Then we find the half value thickness of the standard source thallium using by measuring the thickness of the aluminum, which is the absorber we use, and count 1, count 2 and count 3 are taken. Then the mean count is calculated and the count per second is calculated. Then a graph is plotted between the thickness value on x-axis and the count per second value on the y-axis, from which the half value thickness of the standard source can be determined. Using this standard half value thickness, we can determine the range of standard source, since we have the endpoint energy of the known, that is the standard source thallium E0 equal to 0.766. Using the further equation, we can determine the range of the standard source. Now we have to determine the range of the unknown source. For that, repeat the same procedure by placing the unknown beta particle in the place of the known beta particle, and the same measurement readings are taken. Count 1, count 2, count 3, and the mean count is determined. And as earlier, the graph is plotted between thickness and count per second, and then the half value thickness of the unknown source is determined, and using the equation of range of unknown is determined. And finally, the endpoint energy of the unknown source E0 is determined. Now we get the result. The endpoint energy of particle emitted from the unknown beta source. The source that we use here is the endpoint energy depends on the source that we use for the experiment. For this experiment, we used the standard beta source of thallium and the unknown beta source as the cesium, and we had obtained the endpoint energy of the particle emitted from unknown beta particle E0 as 1.788 mega electrovolt. That's all about my talk. Thank you.